All right, today in astronomy, our essential question, today being September 2nd, 2021, how do astronomers use a cosmic distance ladder to determine distances to astronomical objects? We had previously discussed sort of the zeroth rung of the distance ladder being just figuring out how far away is the sun. And that was determined, one of the very first times in the 1700s, looking at a transit of the planet Venus, going in front of the sun, and then measuring that in two different places on Earth, and using Earth as the baseline on the idea of parallax there. Once we know that, we can use parallax again to get to a handful of other stars that are within about 100 parsecs. Okay, so parallax was sort of, we did yesterday with our lab work. We looked at an example of that sort of in the lab. And that's what astronomers use to measure distance to, a handful of stars that are actually about 100 parsecs or so. If you get further away than that, the stars don't move enough for us to observe it. Okay, so remember, we're measuring the apparent change in position relative to more distant background objects, and things further away than that are just so distant that they don't move. Okay, so it's only about a handful of stars there. Is figure out the distance to those stars, like the Hyades is a cluster of stars that's within this range, and so we can work out the distance to the Hyades. And within the Hyades, there are main sequence stars. And so the next rung of the distance ladder, and the one that we've yet to sort of discuss, but you'll have an assignment today where you can sort of focus on this one, is called main sequence fitting. So there are types of stars in the universe, most stars in the universe, that we call main sequence stars. Main sequence stars. If you plot how hot a star is, its temperature, against how luminous it is, how bright it is, you'll realize that there's a pattern there, that stars fall into what's known as a Hertzsprung-Russell diagram. Hertzsprung and Russell were two different astronomers who sort of independently realized this. But I think the ones that we use today, I think is like Russell's version of it. But we still honor them both, and we call it a Hertzsprung-Russell or an HR diagram. And what your assignment is today is to research a Hertzsprung-Russell diagram. So you can queue one up on your own electronic device, or you can use one of the student computers. I think you might have seen like on the whiteboard or on the projector a moment ago that I had one sort of queued up that I can send to the printer. Maybe I already did, I just gotta go pick it up. So, but try to sort of put the notes into your journal sort of about this. Parallax is based on our knowledge of geometry. We understand sort of how the angles change, and we can work out the distance, and it's very well understood. Main sequence fitting is pretty well understood, but the uncertainties get sort of greater and greater the further out into the universe we're measuring. So this is, understood pretty well. Here, the uncertainties we basically don't worry about anymore, because we can measure this with, radar and things like that, as our co-professors mentioned in the video lesson. Main sequence fitting is thanks to 100+ years of astrophysics research. So we've done enough research studying the universe that we can basically fit the stars that we've studied onto a graph, and we realize there's a pattern there. And so when we look at a star and we look at its color tells us its temperature. The HR diagram then allows us to find its corresponding luminosity based on its temperature. So the hottest stars burn blue. So when we see blue stars, we know that it's very hot, and we can work out on an HR diagram how truly powerful they are. What's the actual brightness? That's the luminosity. Flux is how apparently bright the star is. This is always something we can measure here on Earth, right? We always know what the flux of an object is. So if we can deduce the luminosity through an HR diagram, right, by looking at the color of the star. So the color of the star is always observable to us here on Earth. The brightness, the apparent brightness of the star is always observable to us. And we know 2 out of 3 variables, and we can solve for the third one. So using this equation, which was sort of like your kind of mini quiz last Friday, we can work out the distance to a star that has an observable sort of apparent brightness. And our best guess as to its true power thanks to, 100+ years of astrophysics research and what we know about how, the color of a star and therefore its temperature relates to its luminosity. And so that gets us out to really the next galaxy. So there are main sequence stars in the Hyades that we can calibrate to this, and then we find main sequence stars in the Magellanic Clouds, sort of a nearby satellite galaxy, which allows us to sort of realize things like, okay, this is a yellow star. It's probably just like the sun. We know how luminous the sun is, right? So we're assuming that the yellow dwarf stars that are in the Magellanic Clouds are really just as bright as the sun is, right? And we know how truly bright the sun is. And we ask ourselves, then why does it look so dim? Why do these yellow stars appear so dim to us if they're just as bright as the sun? And of course, the answer is because they're much further away than the sun, right? They're a whole galaxy over. And this mathematics allows us to calculate exactly what that distance is. And so astronomers are clever about how we sort of figure out the distance to something like a star in a nearby galaxy, because there's no ruler that big, right? We can't actually measure it. We got to be clever, and we got to rely on how things appear to us and what we can sort of deduce based on our understanding. And one idea builds on the next. And so for the remainder of class, what I'd like you to do, if you're sort of watching along at home, go ahead and research a Hertzsprung-Russell diagram. I'm sure you could find countless examples of that figure, and try to get some notes in your journal on that. And it all belongs on rung 2 of the distance ladder. This only gets us to a very nearby place in the universe, but we calibrate, sort of the next rung against that and get further and further out. So this lesson will certainly take us into next week. Measuring distances in astronomy is one of the most difficult things about astronomy. If you look on Focus, you'll see that there are slides connected to the assignment called Distance in Astronomy. Kind of go through those slides, get the notes down. Your grade on that is just sort of the work that you're including inside of your journal, including today's work. If you find a really good one and you want to email me the link to it or the web address where you found it, I will try to just send it to the printer, print it out for you, and that way you could, add that into your journal, or I might print out, a bunch of copies of like a really awesome one.